Thursday evening. We're out of multiple integration. We now begin the final topic of the calculus sequence. We started the semester by studying what? Vectors. How many parameters did a vector have?
2.
Depends on the number of dimensions.
You're thinking of components.
Direction and magnitude, right?
A vector is direction and magnitude, but that's not the parameters. Single parameter, wasn't it? R of t, R of theta. Do we have to have a single parameter? Welcome to multivariate vectors, called vector fields. Or simply a field. So we have to be careful with that. Fields are actually a mathematical object that are different than vector fields. There is a branch called field theory. Right, these would be more of the physical fields. And so you have the gravity field, you have electric field, you have a magnetic field. These are all vector fields. We studied two types of fields in particular, the vector field in R2. All right, so what it does is assigns vector field is an assignment. It assigns a two-dimensional vector to each point. Yeah, so it assigns each ordered pair in R2 to a vector. The vector field in R3 is just going to take each ordered triple and assign to it a vector. Be advised that just because the vector field is an ordered pair could make that a three-dimensional vector. It doesn't have to be two-dimensional. Likewise, f of x, y, z doesn't have to be three-dimensional, it could be two-dimensional.
For the vector field in the third dimension, the d of R2, is that supposed to be d of R3, or should that still be d of R2?
That was the type of that should have been R3. By the way, we've already seen vector fields. What was an operation we studied in partial derivatives?
Directional derivatives?
How did we find a directional derivative? Gradient. The gradient's a vector field called the gradient field. However, that is not the term you're probably familiar with. You're probably more familiar with it being called a conservative field. Conservative fields are extremely important in physics. Gravity is conservative. Electricity is conservative. Magnetism is conservative. That scalar function is called a potential function for the field F, or simply a potential. Right, so any field that can be written as the gradient of a scalar is what's known as conservative. Given a conservative field, is its potential function unique?
My guess is no.
Why do you say no?
All right. Feeling.
Feelings get you into a lot of trouble.
I sure do. And elsewhere. I can't do better than that. It's a hunch.
So can you then come up with two potential functions, two scalar functions that would give you the exact same vector field?
Well, now that doesn't seem like something you'd be able to do.
And when I say a vector field, I'm not referring to the zero field. That's not really a vector field. They are up to a constant. So your potentials can only differ by. And this makes sense. Remember what the gradient does. If you take the partial with respect to any variable of a constant, it's zero. Well, what if we're given a field and we want to determine if it is conservative? This is the cross partial property. If it's two variant, and f of xy is just p of xy, q of xy, then the partial of p with respect to y is equal to the partial of that is a massive error. Partial of p with respect to y is equal to the partial of q with respect to x. What if it's PQR? When you still have the cross partial properties. Right. All of your cross partials have to equal. So partial P partial Y is partial Q partial X. Partial Q partial Z is partial R partial Y. And partial R partial X is partial P partial Z. And in fact, these are if and only if statements. So if the cross partials are equal, it's conservative. That gives us our test. If you're given a vector field to determine if it's conservative, take the cross partials and see if they match. If they do, it's conservative and thus would have a potential. If not, then it's not conservative and no such potential would exist. What's my favorite mathematical operator? That's an operation. The del operator, nabla. We now will learn my two favorite mathematical operations. First is known as the divergence. So you have a vector field, PQR. P of X, Q of Y, I should say PX, QY, RZ. They all exist. The divergence of F is defined as partial P partial X plus partial Q partial Y plus partial R partial Z. Divergence is also written as del dot F. Is that notation familiar to anyone? No? What should well, that's not cross product.
It looks like it.
That's a dot product.
Oh, yeah, that's one.
Is it supposed to remind us Of the directional, okay.
Let's see if this one looks familiar. The curl. Given a vector field PQR.
Crawl.
I'm not an English major, shut up. All the first order partials exist. Then the curl is defined as the vector whose first component is partial r partial y minus partial q partial z. Second component is partial p partial z minus partial r partial x. Third component, partial q partial z minus partial p partial y. That's not right. That's supposed to be partial q partial x. Curl is also written like that. Does that ring a bell?
Crossroads.
True. But do you recognize how that's written? Does that make you think of anything in particular? Oh, what a shame. Do those look familiar? Now that is very upsetting.
Are those like your favorite equations from day one?
But these are probably four of the most important equations in human history. Maxwell said, "Let there be light." These are Maxwell's equations. Which relate E fields and B fields, electric fields and magnetic fields.
Was he the guy who did the Maxwell and Demon experiment? That guy?
That name of the experiment doesn't sound familiar. When was the experiment performed?
I don't remember. It involved two different rooms and cycle energy.
Maybe. But these are from the 1700s, 1800s. Without this discovery, none of this would be possible. We wouldn't have electricity. So I said these are probably the four most important equations in all of human history. This just happens to be called the differential form of Maxwell's equations. There is an integral form as well that we will examine. Epsilon naught and mu naught are universal constants. Let's see if I remember the order. Epsilon naught is the permittivity of free space, and mu naught is the permeability of free space. I think that's the right order. Yes, epsilon naught. I remember my E and M. That's nice. Rho also happens to be a constant. I just don't remember what that constant is. I think it depends on the field.
What about JC?
That is current. That is the current vector. Why we use capital J to represent the current vector when the scalar current is I beats the hell out of me. So we're going to start by plotting a couple of vector fields. Let's see, I think it's this, right? Vector plot. First component. And second component. going to ignore the on the circle for right now. So that's the bare minimum, and then that's what it will give us. There are a ton of options. Obviously, the first options are to turn off the frame and turn on your axes. Let's look at these. No, there are a ton of them. First one I'm going to use. Turn off the vector color function so that you can actually define a color yourself so you don't get those really weird ones.
What did the colors represent? If anything.
Magnitude.
Oh, okay. Huh.
Yeah,
Okay.
the magnitude. Right, because if you notice, they're
Yeah.
all drawn to the same length.
Right, I see.
Vector style. Right, you could then use the vector style to change the color. Yeah, boring. I think the scaling is the one that I'm going to use. Yeah, that would then adjust your magnitudes.
Looks like a modern art installation.
I don't like. So I'm going to stick with the default option of none. We can also choose points. I'm trying both. So it's regular. And so what the vector points option does is choose the points, number, or placement of the arrows. So that's regular. That is typically what I use. But I just saw a new one. I wonder what mesh would look like here. That's actually not bad either. I think I might like that one better. But again, keep in mind that that doesn't show proper scaling. Because that's drawing them all of the same magnitude. Which clearly each vector is not going to be the same magnitude. But it still gives you a general idea of what it's doing. What was there? There was. But they asked us, if I remember correctly, to plot it on a circle. Right, specifically the circle, go away, go away, go away. X squared plus y squared equals 4. Now, of course, this is because I have that set to mesh. Oh dear. Let's probably just get rid of that. Oh. It's not at all what I thought it was going to do. Maybe that is what I wanted. Oh, you know what? I bet it's because this is supposed to be this. Yep, that's what I wanted. I didn't just want it on the boundary of the circle, I want it on the entire circle. What would it look like if I do regular? Kind of like that one better for being on the circle. Let's say we don't want the circle actually plotted. So the region filling style, turn this off, what do you think it's going to do?
I guess nothing.
Gets rid of the shading.
Oh, I didn't notice the shading.
What do you think that's going to do?
Get rid of that line.
Get rid of the boundary. Right, which means I could also just do this, right? Turn the boundary off and keep the shading. Right, or filling. Right, or change the color of the. And so you can do some real fun things with it. But again, I don't know why Mathematica considers that to be pink. That's not pink. Where's my favorite website? Is it not here anymore? Yes, it is. There it is. Ooh, ultra pink. Yes, please. Oi! It's because I did this wrong. It's supposed to be that. What method am I going to go with? So there we go. There's our vector field on the circle. And that is called a spin field. You'll probably figure out why. Here's 3 dimensions. This one's called a radial field. I guess we'll find out why. Pretty much the same options, I believe. Oh, we'll see. That's vector plot 3D. And so again, braces, your 3 components. Now I need to specify a viewing window. And that is technically all we need. View it, turn it. Just like everything with 3D, I'm going to label the axes. And you can probably see why this is called a radial field. Make it so it's not really so like color popping. I think I can do the same thing with the axis style. Yeah, try and make the axes stick out a little bit better. All right, they're all coming away from the origin, right? We can again change the points like we did before. Let's see what the mesh looks like. Oh, I like that a lot better. That is so much better. What would the regular do? Nope. Nope, I definitely like the mesh here. I thought there was a way I could not make them 3D. What if I do this? Yes, arrow, thank you. Which means I no longer need, where is it? That to be like gray, I turn that to black. That kind of blends in with the axes now, so let's just do gray. I personally do not like the 3D vectors, the 3D arrows, which is what it was before. I like these two-dimensional. So I like that a lot better. I think at this point I could then do regular, so it doesn't, now it's not so bad. The regular's not so bad. Right, so in this case, if you notice, it's called radial because look, they're all coming from the origin, right? And they're pointing away from the origin. So this would be repulsive. What do you think a gravity field would look like?
It would be like the opposite of this. It would all be pointing towards the origin.
Gravity field is still radial, but it all points towards the center. So is an electric field and a magnetic field. I kind of like that. I'm going to use that. So again, have some fun with it. Well, vector field is made up of multivariate component functions, right? So can't we take partial derivatives of the component functions? Which means we can take partial derivatives of the vector fields. Here they want second order partial derivatives of A. Oh boy. Oh good, it's only two variant. How many do we have? There's three. That's because mixed partials are equal. Order doesn't matter. That is Claret, right? That's Claret's theorem. But first, we need to find the first orders. How do you think we go about finding a partial derivative of a vector field?
Take the partial derivatives of its components.
It's just the partial derivative of the component functions, right? What is the first component?
4xy minus 4x cubed.
Second component.
Y e to the xy minus y cosine x.
And third component.
2x cosine y.
Partial A, partial Y. What is the first component?
2x squared.
Next component.
X, e, x, y, minus sine of x.
Third component.
Negative sine of y.
Times x squared.
Negative x squared times sine of y.
Oh,
We can now use these to find the second order partials, right? So let's first do partial of A with respect to x twice. First component.
Eight x y minus 12x squared.
What was it?
Oh, 4y minus 12x squared.
Second component.
Y squared e to the xy plus y sine x.
what about the third component?
Two cosine y.
Let's do with respect to y twice. First component.
0.
Ooh, that was hard. Second component.
X squared e to the x1.
Oh, I like this partial. Third component.
X squared cosine. Negative x squared cosine y?
Negative x squared cosine y. Right, then the mixed order. And remember, it doesn't matter. So do you want to look at with respect to x and do it with respect to y? Or do you want to look at the respect to y and do it with respect to x? It doesn't matter. First component. Second component.
xy e to the xy minus cosine x.
You said minus cosine?
Yeah.
How'd you do it? Which one did you?
I'm looking at partial a, partial y, and differentiating with respect to x.
So what did you forget?
For the middle term, chain rule, or
I agree with the minus cosine x. I do agree with the xy e to the xy. But you're missing a term. Isn't that middle component x times e to the xy?
yeah.
Isn't that a product of functions of x?
Yeah, I don't know why I said chain rule, I meant product.
Product rule. So what's missing? Uh-oh. Oh, okay. Cool.
Plus xy e to the x. Wait, no,
Now you already have that term.
plus x e to the x.
All right, so you gave me first times second. First times derivative is second.
Just e to the x1.
Just e to the xy. I gotcha. Make sure you pay attention to that, right? It's a very common mistake with partials. Forget to do product rule, quotient rule. And what's the final component?
Minus 2x sine y.
And there are all the second order partials for A. So nothing new there, right?
I'm missing how we're going from the second of each one down to the combined one.
Well, it's not going from the second.
It's okay.
It goes from the first.
Okay, I'm then. In addition to missing that, I'm missing how we're going from the first to the.
So
last.
remember, order doesn't matter, right?
Right.
So choose an order. Do you want to do X first and then Y, or Y first and then X?
We just did X first and then Y, right? We did okay. Y.
He did Y. It doesn't matter.
Okay.
You'll
Y.
get the exact same thing.
All right. Y.
So look at with respect to Y.
Right.
Differentiate that with respect to X.
Oh. Oh. All right. Oh. All right.
So that was
Oh,
that middle order, by
okay.
the way.
All right. I got it. Thank you.
All right, so nothing new, right? This is what we did this in partial derivatives. Which was between exam 1 and 2. Well, vector fields have all the operations, right? You can add vectors, multiply vectors. You can take a dot product, a cross product, scalar product. This one happens to be a scalar product. I'm gonna find phi times f first, and then go with the partials. Instead of trying to do a scalar product rule 3 times, because it's a freaking third derivative. Well, what was the rule? If you had a vector multiplied by a scalar, how'd you find a scalar product? I don't want to say scalar product. Scalar multiplication. And scalar product's the dot product.
You would just distribute it out between the components of the vector.
So what do you mean by distributed out to each?
Multiply the components of each vector by the scalar.
Right, multiply each component of the vector by the scalar, right? So that'd be what, x squared, y squared, z squared, negative x squared, y to the 4th z, and then x, y cubed, z cubed. Did I do that right?
I think so.
Now to find the partial. Remember, the order in which we take the partial doesn't matter. So what do you want to do first?
Partial Z.
You want to do z first? What's that partial?
Two x squared y squared z negative x squared y to the 4th 3x y cubed z squared.
Odd choice. Take that, differentiate with respect to x. What do you get?
y squared z negative 2x y to the fourth 3 y to the third z squared.
With respect to x again,
4y squared z. Negative 2y to the fourth. And 0.
well, arithmetically, it didn't matter. Your best option would have been to do x first.
Because you would have got 0 earlier.
Again, in this case, it was so simple, arithmetically, it didn't matter. But there might have been functions where that would have saved you a lot of time. And so try to look out for those kind of things. Well, you can see it right off the bat, right? Because there's only one x, which means it's going to have to be 0 if you do it with respect to x twice. Just like if there was no, so let's say there wasn't a z in that second component, then I'd agree, do it with respect to z first, because then that middle component's going to go to 0. Right, so keep an eye out for that. Again, you're not incorrect no matter what order you do. Oh, but we're not done. Didn't ask us just to find the partial. It asks us to find the partial at a point. Why is it lagging? What was that point? 2, negative 1, 1. Well, the good news is no component has x. That makes this easy. Just 4, negative 2, 0. There's definitely something going on with this computer. It's running really slow. What operation is that?
Divergence.
The divergence. How do you find divergence?
Partial x of the first term,
Which is what?
2x z squared, plus partial with respect to y in the second term, which is minus 4y z squared, and then plus x y squared.
And y is at xy squared.
Partial of the third term with respect to z.
There's your divergence.
So it's the second. It's what we did just in the last one, right? Where it's the second, and then over partial x, partial y. Then I'm missing what we just did.
Partial with respect to x of the first term,
Yes.
plus partial with respect to y, the second.
Second term.
Plus, and then third term is partial z.
Wait, okay, got it. That makes sense. Thank you.
Before we start, would this operation even be defined? Why do you say no?
Because when you take the divergence once, you get a scalar. And you can't do it again unless you
Well, that's true.
oh, well, it's not a vector value. Or a vector value function.
What's that? Which is called a gradient field. So wouldn't that be a vector? A vector field? So yes, this is defined. This is divergence of a gradient field. I would agree if that was del dot,
Yeah.
then it definitely would not be defined. So what we have to find first is the gradient field. What is the gradient field?
Um, 18x squared y squared z, comma 12x cubed yz, comma 6x cubed y squared.
Now find the divergence.
Could you explain how you figured out that that's the vector field?
It's the gradient from 4.
Yeah, so you're just taking the partial x, comma, partial y, comma, partial z.
Okay.
If it's 3 variant.
It's
So what's the divergence?
36x y squared z plus 12x cubed z.
Plus what?
12x cubed z.
Oh yeah, another cool operator. Just introducing the operators today. The Laplacian. We're going to prove that the Laplacian of a function is the divergence of the gradient field of the function. So to find out three varied functions, just some function of x, y, and z. Gradient of psi is that right? Now take the divergence. Is that right? But that is this. Written another way. Factor out the psi. Which is the Laplacian of psi as desired. Skip this for right now. I'll come back to it if I have time. I'll just stick this to show that del squared psi equals 0 is called Laplace's equation. It's a partial differential equation. Specifically, it's a second order partial differential equation. there's time. All right, curl. How are we going to find curl?
For the first term, it's partial of the third term with respect to y minus partial of the second term with respect to z.
What is the partial of the third component with respect to y?
2xy and z.
Minus what?
Negative 4y squared z.
What's the next component?
2x squared z minus y squared z.
How'd you get it?
It's the partial of the first term with respect to z minus the partial of the third term with respect to x.
And what's the third component?
Negative. I'll just zero.
I don't think there's any other simplification we can make, so I'm just going to write that as 0 and call it a day. So, by the way, there is a reason why we use the notation we use for divergence and curl. If you look at the divergence, that is a dot product, right? So remember, del is partial x, partial y, partial z. And the dot product is you multiply the first components, second components, the third components, and add them together. Which is kind of what we're doing here. Again, keep in mind we're not really doing a dot product. Right? Operator dot something makes no sense. We just write it that way because it's kind of what we're doing. Right? First operator on the first component, second component operator on the second component, third on the third, and add. Well then, that kind of behaves like a cross product, if you look at it. So instead of memorizing that, you could also perform it like you would a cross product. treat it like that determinant. All right, first component. That minus that. Second component, negative that minus that. And then third component, that minus that. And again, remember, we're not really doing multiplication, right? It's an operation on. So it's not partial x times f2. It's partial x of f2. But they behave so similarly. Right. Which is why I said we, air quotes, factored out a psi. We didn't really factor it out because it's not multiplication. But in terms of how the operators behave, you can do that. Then that partial squared partial x squared plus partial squared partial y squared plus partial squared partial z squared behaves as a single operator. Have I emphasized this problem enough yet?
I think we need a couple more.
I like the rainbow sparkle stuff.
That's Galaxy.
I like the galaxy sparkle.
I think we need a few more.
We're going to prove that the curl of del psi is the zero vector for any function psi. Oh. But del psi is what?
The gradient vector.
What's another term? What's another word for that?
Gradient field.
What's another term?
Vector field.
What was the other term we used for gradient fields? Conservative field. We're going to show that the curl of every conservative field is the zero vector. In other words, there is no curl. Which provides us another test on whether a field is conservative. Take its curl. We're going to get the curl of psi x, psi y, psi z. But the curl partial of the last component with respect to y minus partial of the second component with respect to z partial of the first component with respect to z minus partial of the third component with respect to x, partial of the second component with respect to x, minus partial of the first component with respect to y. What do we notice?
Since it doesn't matter the order you take your partials, partial with respect to two terms is, when you take the difference is 0.
Mixed partials are equal by Clairaut's theorem. And so the proof is complete. There's 10 minutes left. I am not 100% certain I can get through that in 10 minutes. That is left as homework. Ooh. Maybe I'll put that on the final. That's a good idea. So you do have a project due tonight, right? You have a couple homeworks coming up, and don't forget the fourth project as well. There will be one more project after the fourth.